We're going to be going over the demo stuff for the beginning of the projectile unit today. So I have the paper right here in front of me that you guys are going to be doing as well. So we'll just kind of follow along and do it together. So first thing, before you start trying to draw any graphs or anything like that, we're just going to watch this really old video, but we're going to use it. Okay. So the pre-demo question says, watch the video and then describe the motion of the ball. So here we go. Oh, very nice. Let's watch one more time. Ooh, basketball gets thrown up in the air and then it bounces. So pause the video right now and answer pre-demonstration question number 1. And we're back for the graphical analysis. So this is the Vernier video analysis. So we uploaded a video. It's this old video of a guy throwing a basketball, and we're going to do some video analysis on this and use that to make some conclusions about the ball. So what we need to do, here you see this little thing down here. That is a 2-meter stick that we put into the frame. So we're going to highlight the length of that thing, click and drag, and it's going to say, how big is that? That is 2 meters. Okay, and where do we want 0 to be? So I'm going to set the origin. Well, I really care about when the ball leaves the guy's hand. And once it leaves the hand, then it becomes a projectile. So we're going to skip this thing forward. That's annoying. Right when it leaves his hand. Good. And the origin is going to be, let's have it be right when it starts. Let's do the bottom of the ball. All right, so that's 0. And from there, it's going to be basically us just trying to click on the ball at the same exact spot every time. So we're tracking the motion of the ball here. So give it a little click. I'm going to always try to click on the same spot of the ball. So clicking right on the bottom. You can see as I'm clicking, like something on the graph over here is happening. There's some data points being put up there. So we'll talk about those here in a second. So there's all of our clicks. Way too many clicks. I should have fast forwarded that a little bit. But as you can see, all the data points that showed up, this looks kind of cool. So if you look at it, the X position dots are the red dots. And then the Y position, like how high it is, are the blue dots. So let's look at just horizontal stuff for now. Okay. If we have a graph like this, I mean, this is pretty darn straight, right? And anytime we have a straight linear position graph, right, that tells us something really important about the motion of the object. That tells us it's going at a constant velocity, right? Every little chunk of time that this thing moves, it travels the same distance every time. Remember, the slope of this graph should give us velocity. So we can actually click linear fit for this, and we can see what the velocity is. This ball is going forward at a velocity of 3.082 meters per second the entire time. And that's really, really straight. So that's good data. All right. So if we looked at the y velocity, or sorry, the x velocity, if it's a constant velocity graph for the position, then constant velocity should be just a nice flat line. So if I click this and look at x velocity, oh my God, that looks terrible. But look at the scale, right? It goes from 2.7 to 3.5. It's really small. So let's go auto scale from 0. So we're going to make 0, 0 be on the graph. Okay. Cool. It's a little better, right? So the velocity is somewhere around 3-ish, right in the middle. If we drew a line through there to kind of be like the average of all those, that'd be it. All right, which is good because remember in our previous graph, we saw that the velocity was about 3.082. Okay, so there's what our x position versus time graph looks like, and then our x velocity graph, good Lord, would look like this. Okay, now when you draw this on your graph, remember we just want to draw a graph shape. So just make that a flat horizontal line. Okay, now in the y direction, if I'm looking at the y position, that's cool, that goes up and then comes on back down, right? So this is where it left the guy's hand at, and because it falls below that line of where his hand was down to the ground, that's why we finished down at like a negative height. If it thinks 0 is up here, it thinks it finished way down here where it hit the ground. Okay, so yeah, we just know that. Now this shape should look relatively familiar from math class. This is what we call a parabola. So whenever something gets thrown in the air, this is the shape of its path is parabolic. It always looks like a parabola. And that's really, really cool because parabolas have this nice quality to them where everything is perfectly symmetrical, right? However long it takes to go up this first half, it's going to take that same amount to get down to this bottom half, right? However fast it left the guy's hand at, you go to the other side of that parabola and it's going to be that same speed right there. Okay, so parabolas are nice because they are symmetrical. Okay, now this velocity is not constant, right? If we think about what the slope of this line is doing, I actually think I can do that. Let's go. Yeah, if you look at this, the slope right here at each point, right? The slope is 3.8, and then 3.7, 3.6, 3.2, right? It's slowing down each little chunk, and the slope is getting flatter and flatter and flatter until it's all the way flat, almost 0, right? So that means the velocity is slowing down, slowing down, slowing down, 0. So it's at the very top. And then the velocity starts edging down. And so now the ball is speeding up, but it's going in the negative direction. Okay? So our velocity graph is going to start with a big positive. It's going to just steadily go down to 0, and then it's going to cross that 0 line and go negative. So let's see what the velocity graph looks like. Okay. So yeah, it looks pretty much like we talked about. The starts at a big positive, right? I don't need this tangent thing anymore, but starts at a big positive, and then it just continues decreasing all the way past 0. So right here, when it's at 0 velocity, that would be when it's at the very top, right? So this thing, when it's right there, that's at the very top of that thing's path. You can see over here if you watch the ball. Boom. And then it starts going back down. Okay? So remember the slope of this graph, slope of a velocity graph should give me acceleration. So if I look at what the slope is, negative 9.7. Let's make that a little bigger for you guys. Let's see. Make it weirdly big. All right, negative 9.72. That's really close to what it actually is. Remember, if there's only the force of gravity pulling down on this ball the whole time, it should be just falling with an acceleration from gravity, negative 9.8, which we usually round to negative 10. So this is a pretty good bunch of data. But that's what our velocity graph looks like. Our velocity graph starts positive, and it is linear as it goes down to a negative velocity. All right? So we want to make sure we draw those graphs in that little dotted line section. We want to draw those 4 graphs. We got x position, x, good Lord, x velocity, right, the graph shape, and then y position, and the y velocity graph. Okay, 4 separate time graphs. Okay, position versus time and velocity versus time for each x and y direction. Okay, after that we want to answer those questions. Remember, use the graphs and use what we know about motion to answer those post-demonstration questions. All right, but yeah, questions 1 through 11, and yeah, I will see you guys on the other side.